Properties of exponential functions. All right, so we've spent a lot of time talking about polynomial functions, rational functions, and now we're moving into exponential functions. An exponential function is different than a polynomial function in that the variable x is not the base, it is now the exponent. In fact, if you look really closely, exponential functions is what we're looking at. So anyways, exponential functions are going to be functions where the variable is the exponent, not the base. The base itself is going to be a number, and that number does need to be positive. That's what this says. B is greater than 0, so it's saying that the base is positive. And we can't have b be equal to 1. If we were to have b be 1, if we were to have that happen, we would have 1 to the x, which 1 to any number is always 1. So we would have the function y equals 1, and that's just a straight line. Say horizontal line. And that's not what we want here. So the base has to be positive, and it cannot be 1. It can be a number between 0 and 1. It can be a number greater than 1, just can't be negative or equal to 1. So why don't we go ahead and graph two of these exponential functions and just look at what the shape is. So we have a traditional table here, right? We have some x values. We're going to plug them into our exponential function, and then we'll have an x and a y, and we'll plot it on a table. So for this guy here, plugging in -2, so we have 2 to the -2. Negative exponents bring the base down to the denominator. So this is the same as 1 over 2 squared. And 1 over 2 squared is 1/4. So this is the point, -2 comma 1/4. 2 to the -1 is the same as 1 over 2 to the first power, which is 1/2. So we have the point -1 comma 1/2. 2 to the 0 is 1. Anything to the 0 is 1, except for 0 itself. So you have 0 comma 1. 2 to the 1 is just 2. So we have 1 comma 2. 2 squared is 4. 2 comma 4. And 2 cubed is 8. 3 comma 8. So let's go ahead and plot. Let me go ahead and pause. So I've plotted the points, and you can see it's going to get steep really quickly. And it's actually going to do a really interesting thing here. It doesn't matter how negative we get with our exponent. It's never going to make the function negative. We're never going to see a negative y value. Putting a negative in the exponent doesn't make the number itself negative. It just brings the base down to the denominator. So what you end up with here is a horizontal asymptote at y equals 0. And the function itself, man, I'm so bad at doing this. There we go. The function itself ends up looking like this. This is the function y equals 2 to the x. It gets really tall really fast. The next number, 2 to the 4th, is going to be 16, then 32, then 64. It just doubles each time. You're multiplying by 2 each time. It's going to get really big really fast. So that's interesting. That's interesting, right? Let's go ahead and look at the other function, 1/2 raised to the x. All right, so we are plugging in -3. So we have 1/2 to the -3. The rule with negative exponents, by the way, if you have x to the -a, this is 1 over x to the a. It's really just the reciprocal, and then the exponent becomes positive. So if you have a fraction, so if you have something like 7/2 to the -1, this right here would flip the fraction and make the exponent positive. And maybe it would be better if I used a number other than 1. So 7/2 raised to the -2 is the same thing as flipping the fraction, taking the reciprocal, and making the exponent positive. So if I'm looking at 1/2 raised to the -3, move you over a little bit, this is the same thing as the reciprocal of 1/2, which is 2, raised to the +3. Reciprocal, make the exponent positive. So this is the point -3, 8. If we take 1/2 and raise it to the -2, that's the same thing as 2 squared, which is 4. So -2, 4. 1/2 to the -1 is 2 to the +1, so just 2. -1, 2. 1/2 to the 0 is 1, much like anything raised to the 0. 1/2 raised to the first power is 1/2. So we have 1, 1/2. And 1/2 raised to the second power is going to be 1/4. So we have 2, 1/4. I'm going to go ahead and plot the points. So you'll see something interesting. This guy looks a little bit different. He's still going to have a horizontal asymptote at y = 0, but he no longer goes from being small to being big. He goes from being big to being small. And it's also interesting that if you look at these y values from 2 to the x, the y values from 1/2 raised to the x are the same values in reverse. And that's not a coincidence. 1/2 raised to the x is the same thing as 2 raised to the -x. And that, if we remember back to our transformations that we talked about many, many sections ago, when you have a negative inside the function like that, it reflects over the y-axis. So a negative out front of the function would reflect over the x, a negative inside the function reflects over the y. And that's exactly what happened here, right? We took this function y = 2 to the x and we reflected it over the y-axis. So it's interesting, right? When we have a base that's bigger than 1, which is what this 2 to the x is, it's going to start really small when you have these negative exponents, and then it's going to get really big as you have positive exponents. And if you have a function where the base is less than 1, but still greater than 0, because that's part of our requirements, it's going to start really big and get really small. This is an important feature of these exponential functions and the shape that they make. So let's scroll down a little bit. The base exponential function, f of x = b to the x, has some properties, some fun properties here. The domain is everything. We can plug anything into an exponential function. It's always going to be -infinity to infinity. The range of a exponential function that hasn't been shifted around at all is going to be 0 to infinity. Those are the y values. The y values, they don't touch 0, right? We have a parenthesis, not a bracket. If we had a bracket, that would mean that we would hit the x-axis, and we don't. So that is not part of the range. There's a y-intercept at 0, 1, and I want to talk about why that would be. So the y-intercept is when x = 0. This is our function right here. So if we plug in 0, f of 0, this is b to the 0, and anything to the 0 is 1. That means the point 0, 1 is on the graph of f. We also have the point 1, a. That should say b. That should say b. I changed this worksheet. I should fix that. I changed this worksheet just recently to change it to bb. This point right here, if you plug 1 into the function, you get b to the 1, which is just b. So that's going to be the point 1 comma b. And if you plug -1 in to the function f of -1, you get b to the -1, which is the reciprocal of b, 1 over b. So you get the point -1 comma 1 over b. Now, really, I just look at this as the reciprocal of b. I don't really think of it as 1 over b, but reciprocal of b. But that gives you a total of 3 points on the graph. The horizontal asymptote is at y equals 0. And then the shape of the graph is dependent on whether the base is between 0 and 1 or greater than 1. So if your base is greater than 1, which is what b greater than 1 means, maybe I'll write base greater than 1. Base greater than 1. You're going to have this increasing shape here. On the other hand, if your base is between 0 and 1, it's going to decrease. Right? Base greater than 1, base between 0 and 1. Now, I mention this, especially these points, because it's really important. I can give you just a basic graph, and I can then give 3 points immediately on it. So if I'm looking at, let's say, f of x equals 7 to the x, this guy is going to have 1 comma 0, because they all have the intercept. Oh, sorry, 0 comma 1. 0 comma 1. They all have y-intercept 0. 1. They all have y-intercept 1. And then I know the point 1 comma a, 1 comma b, so 1 comma 7 is on the graph, and -1 comma 1 over 7. Right? Boop, boop, boop. This is the point 1 comma b. This is the point -1 comma reciprocal of b. I could look at the graph. F of x equals 2/5 raised to the x. I would know that the y-intercept is at 1. There would be a point at 1 comma 2/5. And there would be another point at -1 comma 5/2. It just gives you, 3 quick points that we can put on a graph. This is the 1 comma b. This is -1 comma reciprocal of b. It's a really useful thing. And you'll especially see that as we get into the graphing videos. Then there's one last thing to introduce, and it is the special number e. So e is a number, much like pi. It is irrational, much like pi. It's the number 2.71838, goes on forever. There is no end to it, just like pi. That's what it means to be irrational. This number comes from calculus. It's derived by taking this expression 1 plus 1 over n all raised to the n and letting n get huge. So as n goes to infinity, as we make this number n just ginormous, it's going to become what we know as e. E is called the natural base, and y equals e to the x is called the natural exponential function. It looks like any other function. This is just a number, 2.7. However, it has a lot of applications, especially in biology, in nature. There's a lot of applications that we get from this y equals e to the x function. In calculus, this is going to be your favorite function of all time, because his derivative, which you'll learn in calculus, is e to the x. It's amazing. Great function. It's important to know that this e number exists. You'll have some problems on it. And then we'll be using e in later sections as well. Here's a few pictures of graphs just to kind of compare the different bases. So y equals e to the x, again, this is like 2.7 raised to the x. That's just going to fall in line with all these other exponential functions. The bigger your base, the steeper it grows. So notice that y equals 10 to the x is going to grow a lot faster than y equals 2 to the x. But they all have that same general shape there. E, of course, 2.7 greater than 1, which is why it makes this shape. On the other hand, if we were to boom, let's do it this way. If we were to take 1 over e raised to the x, it would make this shape over here, because 1 over e would be a number less than 1. All right, so that's it for just this basic intro to exponential functions. In the next video, we're going to talk about graphing. It'll be a lot of fun. I'll see you in that video. Bye.